Okay, so let's get to our birthday puzzle. How many people have to be in a room so the probability that two of them have the same birthday is at least 1/2? Let's try to calculate it. Actually, when I'm teaching this, not in distance but in class, sometimes we try to do it kind of in real time. I ask who has a birthday January, which week, which day, and last time, by the time we got to the middle of February, we had two people with a birthday on the same day, and the two people didn't know each other. They were quite happy about that. So, one thing, let's kind of phrase the problem a little bit more carefully to make it harder on us to have two people with the same birthday. If we have twins in the room, then their birthday would be on the same day, but not because of some probability quirk, but because they're twins. So let's make our life harder by saying that there are no twins. And let's consider all days equally likely, even though, again, this is not necessarily the case. There is some statistics that some times of the year there are a lot more babies born than other times of the year. And to make life even harder, let's say that some people can have birthday on February 29th, so we are considering leap years. So again, start with the assumption that every person, a random person, has probability of 1/366 to have a birthday on any given day. So let's talk about how we would calculate how many people would have birthday on the same day. But actually, let's instead calculate the probability that people have birthday on different days. That's a bit easier. So what is the probability that two people have birthday on the same day? Well, you select the day for the first person and you make sure that the second person, and you check with the probability that the second person has a birthday on the same day. Or actually, in this case, let's do different. So with the probability that the second person has a birthday on a different day, that would be 365/366, because this is all days in a year minus the day on which the first person had the birthday. So the first person has a choice of all the days in the year, second person has a choice of all but one, third person has a choice of all but 2 days of the year. So if you count the number of combinations of distinct birthdays of I people by our permutations, well, we get 366 times 365 times and so on. For the person I, it will be 366 minus I plus 1. And the plus 1 there is because we are considered starting with person number 1, but person number 1 has 366 minus 0 possibilities. And remember, probability of two events both happening by the product rule is the product of their probabilities. So now we could write a formula of probability that the I people have all different birthdays. It will be, well, 366/366, that gives us 1, then times 365/366 times 364/366, and so on up to 366 minus I plus 1/366. And the probability that at least 2 out of those I people have the same birthday is just 1 minus this number. And if you do the calculation is not entirely straightforward, but you could do it. This works out to be about 23 people. So think about it. There are 366 days in a year. That's pretty big. But if you have only 23 people, you have 1/2 probability that 2 of them have the birthday on the same day. And if you want to generalize it, then in general it would be roughly, well, kind of roughly, square root of the number of people. square root of the number of possibilities. But that's why I'm referring to it as paradox, because people do find it surprising that in order to have probability half, which is pretty big probability of having two people with the same birthday out of such an unlikely events as having a birthday, well, the probability is 1 over 366, still you get a pretty decent number of 23. And by the way, this is one place where people who haven't seen probability sometimes get kind of a little bit uneasy with probabilistic reasoning. So you might have heard of people reading something in the news saying, oh no, what's the chance of this happening? But you know what, you have so many different things that can happen that the chances of at least one of them happening are pretty good. So what's the chances that two people that were born in the same village meet again in a village half the world away? You say, well, this is probably tiny, but think about it. There are lots of people that are being born in the same village and a lot of places for them to meet. Meeting for people from two specific people from one specific village meeting in another specific place, yeah, that's pretty tiny. But if you look at all the people in the world and all the possible places where they could be born and all possible places where they can meet and use the birthday paradox, then it's not too bad. So next time you read in the news or talk to somebody about some very unlikely coincidence, think about the birthday paradox and ask yourself, is this coincidence really that unlikely if I consider all possible things this coincidence could have come about? Okay, so for the next time, let's do a different puzzle. This unit is great because there are lots and lots of puzzles that we could do. So in our own program, the Monty Hall, there was the game that people played on the TV. Let's make a deal. There are 3 doors. Behind 2 doors are goats, and behind 1 door is a car. And the player, for some reason, wants to be in a car rather than goats. I don't know. Goats are also nice. But let's say a player wants to be in a car. And the way the game goes, the player is supposed to pick a door, 1 out of the 3. And they look identical. After the player picks the door, for example, player says, I think the car is behind door number 2. The host opens another door and shows goat behind that door and asks the player, okay, do you want to stick with saying that the car is behind door number 2, or do you want to change and now say that the car is behind door number 1? Here is a logic and probability question for you. Is it better for the player to switch, or does it matter, or should she just stick with her choice? What do you think?